Hey everyone, I am Dashni K. Today we are going to break down the A-star search algorithm, which is one of the most popular and powerful pathfinding techniques used in artificial intelligence and games. By the end of this video, you will be able to understand how it works exactly and why it is so efficient. Without any further ado, let us dive into the concepts. So, A-star search algorithm is a widely used informed search technique in artificial intelligence. In artificial intelligence, there are two types of search strategies. One is the uninformed search strategy, and the other one is the informed search strategy. In uninformed search strategy, the agent has to start from the starting node and reach the goal node without using any heuristic values, which are additional information. So the agent will start exploring nodes blindly, and hence uninformed search strategies are also known as blind search strategy. In informed search strategy, the agent has access to some additional information or heuristics to guide its search process. So the agent will be able to find the shortest path between the starting node and the goal node and provide an optimal solution. So A-star search algorithm is a popular and informed search technique example, whereas breadth first search, depth first search, uniform cost search, and iterative deepening are examples of uninformed search strategies. So, A-star search algorithm combines the strengths of Dijkstra's algorithm for optimality and greedy best first search for efficiency. It utilizes heuristic values to guide the search process towards the goal efficiently. It plays a vital role in pathfinding and graph traversal problems. So, in order to understand the A-star search algorithm, let us take a simple example. So this is the graph I have chosen. In this graph, there are seven nodes, which are A, B, C, D, E, F, and Z. A is the starting node, and Z is the goal node. And there are a bunch of values in this graph. The values which is in blue color are called the heuristic values or heuristic function. It is the cost of the path between the current node and the goal node, and the values in purple color denote the cost function and is denoted by g of n. So it is the cost of the path between the starting node to the current node. So for the graph I have shown in the previous slide, I have drawn the search tree. From this graph you can observe that A is the parent for B, C, and D nodes. So that is what is depicted here. Whereas for B, there are two nodes branching out from B, which are A and D. But since A is already the parent of B, we only take E as its child. So for each of the nodes, I have generated the successors, that is the child nodes. And for each node there is a value represented. It is known as f of n, which is the summation of g of n and h of n for each node. So after constructing the search tree, I have drawn the table for A star search algorithm. In this table, you can observe that there are two main columns, the open column and the closed column. The open column has four subcolumns: node, G of n, H of n, and F of n. The node subcolumn of the open column represents the nodes which we are going to expand. G of n represents the cost function, H of n represents the heuristic function, F of n is the summation of G of n and H of n. In the closed column, there are two subcolumns, node and parent. The node subcolumn stores the nodes which have been expanded, and the parent subcolumn stores the nodes which are the parent of the expanded nodes. So initially, we will start exploring the starting node, which is A. As we have not expanded any other nodes, the node subcolumn for closed column will be empty. You can observe from the search tree that there are three children for A, which is B, C, and D. Each of the children have a f of n value associated with it. C has the least f of n value, so I will write C first. B has the second least f of n value, so I will write B in the second place. And D has the highest f of n value, so I will write it in the third place. So the g of n for C will be 4, as the cost of the path between A and C is 4, so I will write 4. And the h of n value for C is 18, so I will write 18. And the f of n is the summation of g of n and h of n, which is 18 plus 4, which gives 22. Similarly, for B, I will calculate the g of n by finding the cost of the path between A and B, which is 9. And the heuristic value for B is 14. So 9 plus 14 will give 23 as my f of n for B. Similarly, for D, I will find the cost of the path between the parent node and the current node, which is 7. And the heuristic value for D is 18. So 7 plus 18 will give 25. After summing up all the values, I will arrange them in the ascending order. Uh, so uh, I will get the order as C, B, D. 22 is the f of n value for C, 23 is the f of n value for B, and 25 is the f of n value for D. As I have explored A, I will store it in the closed node column. Since A has no parent, I will leave it as empty. You should note that we have to start expanding the nodes which has the least f of n value. You can observe here that C has the least f of n value. So I will start exploring C first. So C has two children, E and F, with f of n values as 26 and 24 respectively. We have to write the children of C as well as the leftover nodes of the previous step. So I will write the nodes as B, F, D, E, where F and E are the children of C. So B will have a g of n as 9 from the previous step, h of n as 14, which will give a f of n as 23. F, which is a children of C, will have a g of n of 16. Since the cost of the path between A to F through C will be 4 plus 12, which is 16. And F has a heuristic value of 8. So 16 plus 8 will give 24. Similarly, for D, we will take it from the previous step. The G of n is 7, the H of n is 18, and the f of n will be 25. Next, E is the children of C. So we will take the path as A, C, E. So the cost of the path from A to E through C will be 4 plus 17, which is 21. And it's the heuristic value of E is 5. So 21 plus 5 will give 26 as the f of n value for E. After the summation, we will arrange it in ascending order. So I will get the order as B, F, D, E. Since I have expanded C, I will write it in the closed node column. And A is the parent of C. So I will store the parent of C in the parent subcolumn. As you can see here, B has the least f of n. So I will start expanding D in the next step. B has only one child, which is E, with a f of n value as 25. So I have written here E with g of n 20. E has a g of n of 20 because we have to take the path from A to E through B. So A to E through B will have cost function as 9 plus 11, which is 20, and E has a heuristic value of 5. So 20 plus 5 will give f of n as 25. And the other three nodes will be taken from the previous step. So as I have expanded B, I will write it in the closed column. And the parent for B is A. So I will write A in the parent subcolumn. As you can see here, f has the least f of n value. So in the next step, I will start exploring the children of f. F with a value with a f of n value of 24 has children d and z. So I will write d and z here with the leftover nodes from the previous step. Z, which is a child of f, has a g of n as 25. Since we have to take the path from A to Z through C and F, because it is this path A C F Z. So it is 4 plus 12 16, 16 plus 9 25. So I will write 25 here. A important thing to note here is the goal node will always have a heuristic value of 0. As you can see here, it is 0. So 25 plus 0 will give a f of n value as 25. Next, we take the remaining nodes from the previous step and write it here. The another child of f is d with the heuristic with the f of n value as 48. We got this 48 by calculating the cost function and heuristic function. So the cost function of d from A to D will be calculated from this path A to D through C and F. So we have to reach A to D through C and F. So I will take this path. So the cost function will be 4 plus 12, 16, 16 plus 14, which gives 30. And the heuristic value is 18. So 30 plus 18 will give 48. As we have explored f, I will write it in the closed column. Since C is the parent of, as you can see here, C is the parent of f. So I will write C here. If you note carefully, we have three nodes which have the same f of n value. Z, D, and E have the same f of n value of 25. So you might get confused here to expand which node first after arranging it in the ascending order. The thing is, you can choose any node, but I have chosen Z here because we have to find the shortest path between the starting node and the goal node. So as we have already gotten the goal node here, I will start exploring the goal node first instead of other nodes. So the main objective is to find the shortest path. You can also take D first or E first, but we will get a different goal path which may not be optimal. So the solution I'm going to show here will give optimal and the shortest path when we take Z first. So I will start exploring Z in the next step. So Z does not have any children. It is a leaf node. So we will just write it in the closed node and write the remaining nodes from the previous step here. So when we write the goal node in the closed node, it means that we have reached the goal state. So from this search tree we can see that the parent of Z is f. So we will write the parent of Z as f here. So the goal path can be written like this. We know that Z is the goal path, so we will write it in the ending. F is the parent of Z, so we will write F here. And the parent of F is C, so we will write C here. C is the child of A, so we will write A here. We can omit this value because the goal path is ACFZ. It does not involve A and B, so we can omit here. So the final goal path is ACFZ, which provides a optimal and shortest path between A and Z. Now we will look into the practical applications of A star search algorithm. It is used in navigation systems like GPS and Google Maps to compute the shortest, fastest, and alternate routes. It is used in logistics and supply chain, where it optimizes the delivery routes, minimizes the travel cost, and saves time. It is used in robotics and drones to ensure safe and efficient path planning with obstacle avoidance. It is used in video games and provides realistic character movement and intelligent pathfinding. Finally, it is used in network routing, where it finds the least cost path for efficient transfer of data. We will look into the significance of A star search now. A star search algorithm guarantees the optimal path when using an admissible heuristic. A admissible heuristic is the one which never overestimates the cost. It balances efficiency, that is speed, with accuracy in search problems. It is superior to uninformed methods like BFS, DFS, and plain Dijkstra, as A star search algorithm combines the advantages of both Dijkstra algorithm and the greedy best first search algorithm. It is also a widely adopted in real time AI applications such as navigation, robotics, and gaming. We have reached the conclusion now. So, A star search is a powerful informed search algorithm which combines optimality and efficiency. It works by evaluating f of n, which is the summation of g of n and h of n with admissible heuristics. It guarantees an optimal path while reducing unnecessary exploration. It plays a vital role in navigation, robotics, gaming, logistics, and networking. It continues to be a cornerstone in AI driven real world applications. Hope my explanation for A star search algorithm is clear. Thank you.